Okay, so in the previous video, we have seen that if a set A is non-empty, then there exists some element in A. That is, we can choose an element from a non-empty set. And this result was called naturally single choice. And we also mentioned that if we have a finite collection of non-empty sets, where this n can be any natural number, then from each such set we can choose one element. This will be proved, and this has the name finite choice. Then we also mentioned that in place of this, a finite collection of non-empty sets, if we have an infinite collection of non-empty sets, where the number of sets is infinite and each one is non-empty, then we cannot prove that we can choose one element from each such set using only the axioms that we present in this chapter. So for this we need a new axiom which we are going to see in section 8.4, and that is the axiom of choice. The axiom of choice. Now let us move forward and see what the other axioms of axiomatic set theory are. Now before we get to a new axiom, let us look at a remark. So this is remark 318. So what this says is very simple, but nevertheless, let's just see what it says. The empty set is not the same thing as the natural number zero. If you recall, we have already said something about pure set theory, in which all objects are sets. In particular, there we said that 0 is defined to be or is identified with the empty set. 1 is identified with this set, this Singleton set. 2 is identified with this set. Which according to our definition is nothing but this set of two elements. One of them is a set itself. So this is the case if we develop the natural numbers using set theory, or rather using cardinalities of finite sets, but we have not done that. We have taken the different approach of developing the natural numbers using the piano axioms, where the numbers are not considered as sets. They are considered as some objects in their own right. So for us, 0 is different from the empty set. A more accurate remark is this. Rather, 0 is the cardinality of the empty set. Let me wipe this part. So 0 is the cardinality of the empty set. We will discuss cardinalities of finite sets rigorously in section 3.6. So, although we know from our study of naive set theory what cardinality of a finite set is, but we are going to do it again more rigorously in section 3.6, because the way we approach cardinality in naive set theory, that is also naive. Okay, that is not as rigorous as it should be. Anyway, so this was the remark. Let us now move on to a new axiom. So let me write it here. So this will be the third axiom, yes. Let's briefly recall what the first two axioms were. The first one said that sets are objects. This in particular says that if we are given two sets, then I can ask whether one of them is an element of the other or not. And the second axiom said that there is an empty set. Now we want to enlarge our class of sets. So far we have only one set, right? From the point of view of having the sets or constructing the sets, we have only one set, empty set. Everything else about sets that we have stated or we have done, they are of the form if then. Those statements are conditional. If A is a non-empty set, then there is an element. But from the point of view of giving some examples or producing some concrete sets, so far the axioms allow me only one set, empty set. So we naturally want to change this, because if my set theory has only one set, then it's useless, it's rather boring, there's nothing to study. So the next axiom postulates the existence of singleton sets and pair sets. So basically what it says is simple. Let me just first write the name, the title. Singleton sets and pair sets. Given any object A, there exists a set whose only element is A. That is, for any object Y, we have Y belongs to this set if and only if Y is equal to A. We call this set the Singleton set formed by A. Okay, so it just simply says that if we are given an object, then there is a singleton set which has only that object as its element. Like this, for any given objects A and B, there exists a set A comma B whose only elements are A and B, that is for any object y, we have y belongs to this set if and only if y is either equal to A or y is equal to B or both. See, whenever we see or in mathematics, we tacitly assume that it's inclusive or. From mathematical logic, you already know what inclusive or is. Inclusive or means something is true or something else is true or both are true. Okay, so that type of or is here. If we want exclusive or, specifically we will have to explicitly mention that, right? We call this set A comma B the pair set formed by A and B. Okay, so this is the third axiom, which says that for any object there is a singleton set, and for any two given objects A and B there is a pair set. Now recall that when we introduced the second axiom, which postulates the existence of an empty set, after that we remarked that there is only one empty set, which follows from our definition of equality of sets. A similar remark can be made here also, that if we are given an object A, then there is only one singleton set that has A as its element. So that thing comes as remark. Let me see, I should not mess the numbers up. Remark 319. So what this remark says is this: definition (314). If you go back, you can see that this is the definition of equality of two sets. That definition ensures that for a given object A, there is only one singleton set and for given objects A and B, there is only one pair set. Verification of these things I am leaving to you. They are very easy. It's somewhat like how we verify that if we have two empty sets, then they are actually equal. Go back to that and see if you can prove this. If we have two singleton sets, say A1 and A2, for the object, for that single object A, then actually A1 has to be equal to A2. It seems obvious, but nevertheless we have to prove it. Okay. For us, the only obvious things or obvious statements which are left obvious without proof are the axioms. Everything else needs some sort of justification, which ultimately has to come from the axioms. So otherwise our system will be vague. Okay, so this remarks, verification, I leave it to you. Okay. Moreover, there is one more thing. Moreover, this definition 314 also tells us that this pair set is equal to this pair set. Why? Again, same. You have to just show that they are equal. And this pair set consisting of A and A is actually equal to the singleton set. Here also there is a question. Tau asks 1. These Y's also I leave to you. It's very easy to prove why they are so. Now, look at this. See, looking at this, we see that we don't really need the singleton set axiom. It follows from the pair set axiom. How? You see here, what does the singleton set axiom say? It says that if we are given an object, any object A, then there exists a set whose only element is A. Now I have to prove this. Say, I am not given the singleton set axiom. I have to prove that using the pair set axiom. So what I do in pair set axiom, what is given to me? Objects A and B are given to me. Now the statement does not say anything about distinctness of A and B. A and B need not be distinct. You see, for any given objects A and B, they may be the same thing. So if what we do here, we are given A, we consider it twice and consider them as my objects. Then if these two things are given to me, then according to the pair set axiom, I can form this set. And then using definition 314 of equality of sets, you prove this equality. So this set exists, or rather this collection is a set. So I derive singleton set axiom as a consequence of the pair set axiom. Okay. After discussing some more, we will come across something known as the pairwise union axiom. In fact, that is the fourth axiom. That along with the singleton set axiom will give me the pair set axiom. So it's not that singleton set axiom is just a consequence of the pair set axiom. Singleton set axiom coupled with one more axiom, the axiom of pairwise union, gives me pair set axiom. So that's what we get. I mean, that's what we mean when we meant when we state that we are working with an over-complete list of axioms, that some of them are consequences of the others. Now, there we also mentioned that it's done for pedagogical reasons, for the purpose of learning more about set theory. Why? Exactly what reason? You see, because of this, I may decide to remove singleton set axiom. It's not necessary. It comes as a consequence of the pair set axiom. Logically, that should be done. Okay, logically means from the point of view of logic, the subject logic. That is, we don't want an over-complete list of axioms. We just want a list of axioms which is as short as possible. It has as few axioms as possible. What will then happen? Suppose like this, I remove some other axioms also, which eventually will come out as consequences of other axioms. What will then happen? If I remove singleton set axiom, don't consider it as an axiom, it nevertheless is going to make an appearance as a result, as a consequence of the pair set axiom. So by removing it from the list of axioms, I am not actually getting rid of it. I will just have it somewhere else among the results. Now, do you think this is a very deep result? It's almost obvious. See, for a given object A, no matter it is coming as a consequence of the pair set axiom, but after all the result is so natural that we find it somewhat difficult to call it a result of any status. It's almost self-evident. Plus, looking at the fact, or what we are going to look at pretty soon, that it's not the case that this is following from this and that's the only way. This will also follow from this and the pairwise union axiom that we will see. So it's difficult to decide which one to remove and which one to keep. Plus, if we continue stating self-evident things like this one as results and not as axioms, it looks quite bad. So since we are not getting rid of these things and these things will make appearance as self-evident facts, so Tao has decided to keep them as axioms, although some of them follow from other axioms. That's the reason. Okay, so now, okay. So besides this, there is one more point that we should make. See how we are progressing. Forget about the first axiom. What the second axiom tells you, there exists a set with no element, that is the empty set. Then the third axiom is telling you that there are sets with one element, sets with two elements. Next, naturally, we would go on constructing sets with 3 elements, 4 elements, that is triplet sets, quadruplet sets. But then how long shall we do this? I mean, to what extent shall we continue making axioms? We can't keep on making axioms for sets with 4 elements, 5 elements, 6 elements. It will never end, right? So instead of that, we will introduce one axiom which will take care of all these things. That is the axiom of pairwise union. Okay, but before that, let us just see some consequences of this axiom. Okay, so we have an example. This is example 3.1.10. So what this says, since the empty set is an object. Why? This is coming from the first axiom. The empty set is a set that is coming from the second axiom, and because the first axiom says that every set is an object, so empty set is an object. In other words, it can be an element of some set. Set is an object. The above axiom means this one, says that the following sets exist. What sets? This one. How am I getting this set? I am getting this set by considering empty set in place of A and using the Singleton Set Axiom. Similarly, by considering this as an object, I get this set. Okay, just give me a moment. Okay, so I can get this set. Plus, using these objects and using the pair set axiom, I can get this set also. this pair set. If you recall what we were discussing when we said that the empty set and 0 are different objects, this is nothing but our 1, this is 2 in that sense. Now, there is an exercise. This is the second exercise. Have we solved the first exercise? I am not sure. We will see, okay, when we go through the exercises at the end of this section, we will see whether we have solved it or not. This is exercise 312. It asks us to show that these sets are actually distinct. So it says this: using only definition 314, then axiom 3.2, axiom 3.2 and axiom 3.3. Prove that the sets empty set, singleton set consisting of the empty set, this singleton set and this pair set are all distinct. Okay. Say we want to prove this, but we are allowed to use only what we have had so far, nothing else. Okay, that's how axiomatic treatment goes. You assume some things as axioms and everything else should follow from them. So we try to write the solution. First of all, we have to show that the empty set is different from all of this. Okay, since the sets this and this have elements in them, but this does not. The empty set is different from the remaining three. Why? Because of definition 314, by the definition of equality of two sets. You see, for this to be equal to this, since this contains the empty set as an element, this also should have contained empty set as an element. However, by definition, since this is empty, it contains no element. So that's how all these sets are different from the empty set. Now we look at this. Since this is an element in this set. Okay, this is an element in this set. but this is not an element in this set. We have okay, this set also has an element, but that element is this, not this. Okay, these things should be seen carefully, otherwise we will make grave mistakes. Then, since this singleton set is an element in the pair set, say this appears as an element in this set, but that same element does not belong to this set as an element. We have the singleton set not equal to the pair set. So we have proved that this is also different from these two. Finally, we look at this. Finally, since the empty set belongs to the pair set as an element, but it does not belong to this set as an element, we have this singleton set not equal to this pair set. So this completes the solution. So these two are also different from each other. So the four sets are distinct. And here we have used only definition 3.4, which is that of equality of sets, and axiom 3.2 and 3.3 ensure that these are sets. Okay, for that we need axiom 3.2 and 3.3. This one says that empty set exists. This is the singleton set and pair set axiom. Right. Now, okay. So this was the second exercise. Okay, now we have three axioms. Using these three axioms, we can create some quite complicated sets. For example, we can create a set that looks like this. Okay, which looks quite complicated, but actually it has only two elements. One element is this, and the other element is this. So, because we have got only two pair sets and nothing more than that, so anything we do with these axioms, we are bound to get, after all, we are bound to get a set which has at most two elements. But we want to do better than this. For that purpose, we now introduce the fourth axiom. Which is nothing but the definition of union, nevertheless it's an axiom. So this is axiom 3.4. It is called pairwise union, and what it states is this: given sets A and B, there exists a set, this called the union of A and B, that consists of all the elements